Okay, chapter 3. There's something that we call the expected value, which is simply a weighted average. So if you're trying to solve for the expected value, which we call mu of x, this is, of course, a measure of center, then you're going to add up all of the individual values times their individual probabilities. So this is a more sophisticated way of taking an average. So we're used to taking an average by what? You just add up all the numbers, divide by the number of numbers, right? Well, that is assuming that each number has the same probability of occurring. Like it's like throwing them all in a hat and picking them out, right? Now, versus there may be things where there's higher probability of one value to pop up and a lower probability of another value to pop up. So you've got to weight it. So if there's like, 3 times as much possibility of one value to be there versus 1 time possibility of the other value, you've got to weight it. So it's a weighted average. So each value has their potential of popping up a proportion of the whole. And so you multiply each value by that to find the true measure of center. So we can do an example. .16 on page 110, but just note that the actual table is on the previous page that we're referring to. So turn to page 110 in your book when you get a chance. But remember, like I said, the table they're referring to is on the previous page. So if you look at the previous page, there's that table where you have your values of x and your probabilities of x. So each value has its own probability. So to find that weighted average, you're going to say, well, value 1 has a probability of 1%. I'll add it to value 2, which has a probability of 3%. I'll add it to value 3 times what?
13%.
13%. I'll add it to value 4 times
0.25.
0.25 plus 5 times
0.39.
0.39 plus 6 times
0.17.
0.17 plus 7 times
0.02.
0.02. So you multiply them, you add them up, what do you get? .57. Now here's the thing. If you read the problem statement, it was talking about, if you go to the previous page, it says, consider a university having 15,000 students. Let X be the number of courses for which a randomly selected student is registered. And then here's the table. And so they're saying basically being registered in 1 course, it's 1% chance, 2 courses, 3% chance, 3 courses, 13% chance, 4 courses, 25% chance, 5 courses, 39% chance, etc. So, you can see they want you to find the expected value, right, of how many courses a student would take. So the issue with this number is you need to interpret it in the context of the problem. Can a student really take 4.57 courses? No. right? So make a note to yourself to remember to interpret the number in context of the problem. For example, can a student take 4.57 courses? No. So you would probably make a statement more like the average student takes between 4 and 5 classes, right? Or the average student takes 5 classes because it rounds up to 5. So some sort of interpretation in terms of the actual problem. Now, when you have different values with different probabilities of occurring, your variance is calculated differently than before. So to find that variance, which remember is the dispersion, or remember it was like a measure of spread. When you have these numbers that have different probabilities of occurring, then you have to calculate that variance by adding up all the values minus that mean that you got squared, but each one had to be multiplied by its probability. And of course, if you want to find the standard deviation, you just take the square root of the variance. So remember, this is the standard deviation. Which is a representative deviation from the mean. Basically, on average, how far away is each number from the measure of center? Okay, so let's do an example so I can show you how to calculate the variance when there are assigned probabilities to these values. We'll do example 3.24, which occurs on page 114. So turn to page 114 in your book. Example 3.24 is in the middle of the page. It says a library has an upper limit of 6 on the number of DVDs that can be checked out to an individual at one time. Consider only those who currently have DVDs checked out, and let X denote the number of DVDs checked out to a randomly selected individual. So they're saying the probability of a person having only checked out one DVD is 30%. The probability of only checking out 2 DVDs is 25%, 3, 15, 4, 0.05, 5.1, and 6.15. So questions about the table before we move forward, about how to interpret the meaning of that table. You're going to make a table of your own, which might take up some room. Like if you have a chance to turn your page instead of portrait landscape, it might be helpful. So we have all these values: 1, 2, 3, 4, 5, 6. We have the probability of getting all those values: 30%, 25%, 0.15, 0.05, 0.10, 0.15. Questions about where I got those numbers? Always good to check that they add up to 1, so double check that. Do they add up to 1? Yes. To 1, good. All right, so the next column you're going to do is take each individual value and multiply it by its probability, because we're going to need to find that expected value. So 1 times 0.3 is 0.3. What's the next one? Mm-hmm. 0.5, next. .45, next. 0.2, 0.5, point. Try again. 0.9. Questions about how we got those numbers? So to find that weighted average, we just have to add all those numbers up, because basically they're prorated values now. So what do you get when you add them all up? $2.85. So this represents your weighted average. Your next column you're going to do is take each individual value and see how far away they are from the mean that you just calculated. For example, 1 minus 2.85 is negative 1.85. So it is to the left of the mean by 1.85. What's the next number? Negative 0.85. It is to the left of the mean by 0.85. What's the next one? Positive 0.15 is to the right of the mean by 0.15. Next. To the right of the mean by 1.15. Next. $2.15. Next. $3.15. Questions about how we got those numbers? Next thing we're going to do is take all those values that we just got from the previous column and square them. So for the example, if I square the first number, I'm going to get 3.4225. What do you get for the next one? 0.7225. Next. 0.0225. Next. 1.3225. Next. 4.6225. Next. 9.9225. Questions about how we got those numbers? Okay, after we've done that, we're going to take the value that we just got from that column and multiply each value by the probability of them occurring. So I'm going to take my column that I just got and multiply by that P of X column. So 30% of 3. So it's 1.02675. What do you get for the next one? $0.180625. Next. 0.003375. Next. So we're prorating these deviations based on the probability that they are to occur. We're multiplying that P of X column by the last column we just did. You get 0.066125. Next. 0.46225. Last. 1.488375. Add all of those up, and that will give us our variance. Our variance ends up being 3.2275. Questions about how we got that number? Okay, and now to find the standard deviation, we simply take the square root of that variance. So what do you get? 1.8. Okay, always bring it back into the context of the problem. So you might say that the expected number of DVDs rented is the average 2.85 plus or minus 1.80. Okay, you could put that, you could even bring it further and say like 3 plus or minus 2, right? Because you can't actually rent 2.85 DVDs, right? So 3 plus or minus 2. So you would say maybe it ranges between 1 and 5, right? So I will say that there is also, if you want to check out in the book, there's also what they call a shortcut. I don't know how much time it really saves you, but there's also a shortcut method that you can find on page 115 if you want to look at that. Questions so far? Would we round? I would show your work with all these decimal places and stuff. And then if you wanted to write your final statement rounded because of the fact that it's a DVD and you can't round a fraction of a DVD, then that's totally fine. But I would want to see, you know, your 2.85 on the page somewhere and your 1.8 on the page somewhere. And then when you make your sentence, you could round if you wanted. Okay. So there is something called a binomial experiment. So using your word parts, what do you think binomial means?
Numbers.
Two numbers. Very good. And what we're referring to in this class is something sort of like you have some sort of success or failure, meaning flipping a coin, right? Heads, tails, flipping a switch on, off. Okay. It's black, white. It's got to be success, failure, whatever in the context of our problem. Like if we're trying to shoot a basketball hoop, did we make it or did we not make it? That kind of thing. Okay. Yes, no, on, off, etc. So you can write example, flipping a coin, a light on or off, etc. Can you think of another example? Pass fail of your class. Very good. Okay, what else? Turning a mirror, do you mean like the reflective side and the non-reflective side? Okay, yeah. Okay, makes sense, guys? Okay, so when you're trying to when you're doing a binomial experiment, you're trying to calculate the probability of like a certain, let's say I wanted to like flip 100 coins and what's the probability of like 30 of them being heads, etc. Or I have a number of students, what's the probability of this many of them failing the class, or whatever the on, off, yes, no experiment is, your probability of that occurring is going to look like this. And I'll explain what each number represents. So the N stands for the total number of trials. So if I'm going to flip a coin 100 times, that would be 100. The X stands for how many of them I want to be a success. So if I flip a coin 100 times, what's the probability of 30 of them being heads? That 30 would be the X. So it's our number of successes that we're looking for. P represents the probability of that thing having it, the probability of the success. So if I'm talking heads, tails, it's 50%, but you can still have things that are binomial that have uneven probabilities of occurring, right? So it's whatever the probability is of your success. And essentially, the rest of that is the probability of the failure, right? Because 1 minus the probability of success is the probability of the failure, which is why we have n minus x over there, because it's everything else. So it's basically number of successes with the probability of success and the number of failures with the probability of failure. So for example, if you flip a coin 6 times, and I wanted to know what's the probability of exactly 3 heads when you flip the coin. What is n in this problem? What is x in this problem? What is p in this problem? %. It's not 3 out of 6. It's 50%, meaning in any time you flip a coin, it's 50% chance that you get a heads, right? Anytime you flip a coin. That's the probability I'm referring to. So you would show your work by laying that all out, and you'd say the probability of getting 3 heads is equal to 6C3, and then 0.5 raised to the 3, and 1 minus 0.5, which is also 0.5, raised to the 6 minus 3, which is also 3. Well, a coin has 2 sides, heads, tails. The coin could be rigged, and then therefore getting a heads maybe is higher chance or tails higher chance, and they'd have to state that. Like a weighted coin, right? They'd have to state that. What do you get? You should be able to enter all of this in one fell swoop on your calculator if you know how to use it. Try again. Try again. This is a 3. You're not going to have your classmates to do the work for you, so you ought to try and do it yourself right now. Yeah, that's correct. 0.3125. Questions about how we got that number? What if I said, what's the probability of at most? If I said the words at most 5 heads. What does that mean? Okay, so hold on. Sorry, there was a question about what buttons are we using on the calculator. So you should have an NCR or an NPR button on your calculator. If it's the TI-36X Pro, if you go to the 8, go up 3-ish, 1, 2, 3 buttons, you'll see the NCR, NPR button. So you can press that if you press it once, it's factorial. If you press it twice, it's NCR, and if you press it 3 times, it's NPR. So the way to do it is you type in 6 and then press that button twice, and you type in 3, and that would be how you do NCR. You're also multiplying by 0.5 raised to the, so the raised to the button, if you go to the 7 and go left and go up, that's the X to the button, and you're raising it to 3. Okay, so all of that should be able to be multiplied together. Now, someone was about to answer me with, how do you interpret at most 5 heads?
Up to 5, but not 6.
Very good, not 6. So it would include no heads. It would include 1 head, 2 heads, 3 heads, 4 heads, or 5 heads, but it would not include 6 heads, right? Now, if you're trying to add up all those probabilities, it'd take a lot of work. 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads. You'd have to do 6 calculations and add them all up. Or you could use the complement rule, because essentially it's including everything but the 6 heads probability, right? So you could calculate the 6 heads probability and just subtract it from 1, because all the probabilities add up to 1. And therefore, you'd have to do less work. So when they ask for the probability of at most 5, you could say, well, I'm saying I want X to be less than or equal to 5, correct? Which means essentially I'm taking 100% of the probability and subtracting out simply the probability that X is 6, because that's the only one we don't want. So we can do 1 minus, and someone help me fill this out using the equation above. How would you fill out the probability that X is exactly 6? How do I fill it out? Okay, so we've got 6C6, that's correct. And then 0.5, how many successes do we want? Yes, the same amount of same amount of flips. We want 6 successes, and therefore, how many failures would there be? 0 failures. Okay. Success, success, failure, failure. So we've got 1 minus, what number do you get there for all that stuff in the brackets? 0.015625. So after you subtract that, what do you get for the total? Zero 0.984375. Okay, sorry, to be clear that this whole lecture is not only including chapter 3, but it's also including chapter 4. So you might want to go back up to your notes and label it as chapters 3 through 4. Just FYI. Which, when I told you for this weekend, did I tell you? Yes, I told you to read both chapters 3 and 4. Okay. Okay, so someone help me out. Take a shot at interpreting this number. What does this mean? Practically 100%. Okay. But what does it mean? Bring it into the context of the problem. Yes, therefore, those are the 3 dots. Therefore, a number is useless unless you know what it means. What does it mean? 98% chance that you will get at most 5 heads. Exactly. So there's a 98% chance you will get at most 5 heads. And what we mean by that is either 0, 1, 2, 3, 4, or 5. When you flip a coin, 6 times. It would be very weird if you flipped a coin 6 times and you got 6 heads, right? You would not expect that. Make a note that for a binomial experiment, your expected value, or basically your mean, right, is just going to be n times p. So your number of trials times the probability of a success. And then you would find the variance of a binomial experiment, just n times p times 1 minus p. And so, or a lot of times, sometimes for me, like I like to define success and failure, for example. So I'll just use Q as failure. So Q meaning not P, right? 1 minus P. So then you can just say the variance is, I don't want to write it like that. I don't want to be confusing. The variance is NPQ. So sometimes it's just like easier for me, NPQ. So P is probability of success, Q probability of failure, right? Because it's everything else, NPQ. So then if you wanted the standard deviation, it would be the square root of NPQ, of course, because you're just taking the square root of the variance. So for example, if we were going to flip a coin 100 times, let's see if we can figure out what each of these variables would be. So how would you calculate the mean? Okay, I found Windows. I have Windows 10 Enterprise. Isn't that good? It says 2018 though. I guess that's kind of old. It's 100 times 0.5. So that would be, we would expect 50 heads, which makes sense, right? If we flip 100 coins, we would expect 50 heads. We know it's not going to be perfectly 50 heads. We know that there's going to be some variance there. So let's calculate the variance. How do you do that? How do you calculate the variance?
Isn't it the sum of x minus your mu squared plus px?
So for a binomial experiment, we're just going to follow this equation right here for variance.
Okay.
So how would we fill that out?
So the n is 100 and the p is 50, if I'm not wrong, and the other one minus 50.
Right, which ends up being 50 as well. So what's your variance?
And then we have to square
25?
it.
Yes, so it'll be 25 heads for the variance, and then you're right, you have to square root it for the standard deviation. So it's just the square root of 25, which is
5.
5. So what we would say in a binomial experiment is that if we flip 100 coins, this makes sense. You should expect 50 plus or minus 5 heads when you flip 100 coins. Does that sound intuitively correct, right? You know you're not going to get exactly 50 heads, but you know it'll be around 50. So you would not be flabbergasted or surprised if you got 45. You would not be surprised if you got 55, right? You'd be like, that's about what I would have expected. Questions about that? I think this is the last topic I want to talk about for chapter 3, and then we'll move on to chapter 4, which is the Poisson distribution. The Poisson distribution, P e to the negative mu times mu to the x, well, let me be very neat here, divided by x factorial. X stands for the exact number of successes. So open up your book. Open up your book. And let's do example 3.38 on page 132. So turn to page 132 in your book. We're doing example 3.38, which is in the middle of the page. And it says, let X denote the number of traps or defects of a certain kind in a particular type of metal oxide semiconductor transistor, and suppose it has a Poisson distribution of mu is 2. The Poisson model is suggested in this article. We changed the value of the parameter for the computational ease. Okay, whatever. So if they wanted the probability that there are exactly 3 traps. Okay, so what they're saying is the expected value of this Poisson distribution is 2. We want the probability of getting 3. So help me fill this out. Ready, set, go. What do I write?
It's e to the power of minus 2 times 2 to the power of 3 over 3 factorials.
Very good. You should be able to enter all of that into your calculator all at once using your fraction button, your exponent button, and your factorial button. What do you get? $0.180. What does that number mean? How can you interpret it in context of this problem? Always go back to the problem statement in the book and remind yourself, what were they asking me to do? And how can you summarize it in your own words? Probability of exactly 3 traps. Yeah, yes, exactly 3 traps. So the probability of exactly 3 traps is 18%. So here are some notes about when to use Poisson distribution. Use Poisson for binomial distributions where the following are true. You are doing more than 50 trials, and your expected value is less than 5. So remember, this is really just your mu. Or expected value. So if they say, if you can tell it's binomial, on, off, yes, no, defect, not defect, right? That's number 1. If you're doing more than 50 trials, it's number 2. And if the expected value is less than 5, n times p less than 5, number 3, that's when you know to use the Poisson distribution equation. And they'll say, now, knowing all these things, what's the expected value of getting this many, etc. Again, if you can tell it's binomial, if you're doing more than 50 trials, and the expected value is less than 5, and then they say, what's the probability of getting exactly X? And when they say that, that's how you know to do Poisson.